Hi, this is Dr. B.J. Swaraprasad, Professor of Civil Engineering, G. Polarity Engineering College, Autonomous, Kurnool. This particular video related to the course Design and Drawing of Hydraulic Structures. So in this particular video or module, I am going to explain one of the structures, hydraulic structures called surplus weir. Both design and drawing of surplus weir. So it may covers 2 or 3 parts. In the first part, let us discuss some of the important design components of the surplus weir. So as I mentioned earlier, this entire course of DDHS is divided into number of modules. Earlier the module 1 is introduction to DDHS. Now in the present module, module 2, I am going to discuss about the surplus weir, both design and drawing. Since it takes more time, it is better to divide this module into number of parts. In this video, I will try to cover the first part of this surplus weir, which may contains the design of weir wall and some other components. So surplus weir, in which part 1 consists of design of weir wall, abutment, wing wall and return wall. So this is the content related to the surplus weir or the various topics to be discussed for the design of surplus weir. See, first of all, as part of introduction, surplus weir, as the title is the surplus weir. So weir is, you are all aware about the weir. Weir is the solid obstruction or the solid wall constructed across the flow passage, whether it may be canal or a river or a small stream or even for a tank. So coming to the surplus weir, it is the weir to discharge the surplus water or excess water beyond the required storage of the tank. Say for example, if a particular tank, a certain storage capacity will be there. So if water enter into the tank beyond that capacity of the tank, the surplus water or flood water has to be discharged downstream smoothly and safely, for which the structure is required. The structure is called surplus weir. So in this module or in this video, we are going to discuss the detailed design of surplus weir. So the introduction, estimation of flood discharge, selection of type of work, and length of the surplus weir, crest width of the weir, base width of the weir, and some other protective works like abutments, wing walls, return walls and aprons. So these are the major topics to be covered for the design of surplus weir. As you know the definition of surplus weir, the main component part of this structure is weir wall only, no doubt. Weir wall is also known as body wall. Weir wall is also known as body wall. Similarly, abutments, wing walls, return walls, these all comes under protective works, even solid apron also. Of course, some other additional protective works like revetment and bed pitching also to be provided. And at the end, the specifications required for construction of these components of the structure. This diagram shows the surplus weir, longitudinal section of the surplus weir. So this part is the weir wall or body wall. Subsequently, abutments. At both ends of the weir wall we have the abutments, and also wing walls, both again upstream side as well as the downstream side, and also return wall, etc. So this picture shows an overview of the structure in which the weir wall, abutments, wing walls, both upstream and downstream, and return walls, solid apron, etc. Further clarification, you can see this figure also. This is the actual surplus weir existing in the field. One of the village tanks having this surplus weir in this diagram or in this picture, we can clearly observe this is the weir wall, this is the weir wall, longitudinal view of the weir wall. Subsequently, both sides, both ends of the weir wall, we have the abutments, wing walls and returns, etc. So this is the natural picture which has taken from a village tank which is located in Prakasam district. Now coming to the problem statement. For every structure we need to design. So design problem or problem statement itself consists of lot of information or data. So first of all, we should understand the given data properly. So as our aim is to design the surplus weir in detail. So that means all the component parts of the surplus weir has to be designed, for which what is the actual data or information required, that may be mentioned in the problem statement. That's why the problem statement itself, it consists of a lot of information. So let us go through this problem statement first. So the problem statement is like this: design the surplus work of a tank forming part of chain of tanks. So each and every sentence you have to understand from this problem statement. The first statement is design the surplus work of the tank forming part of the chain of the tanks. I will explain later. The combined catchment area of the group of tanks is 25.89 square kilometers, and the area of the catchment intercepted by the upper tanks is 20.71 square kilometers. So two areas has two values of catchment areas has been given. So we have to observe these two also. It is decided to store water in the tank to a level of plus 12 meters, that is elevation, or a reduced level as plus 12 meter above MSL, mean sea level, limiting the submersion of foreshore lands up to a level of plus 12.75 meters above the MSL. If you observe here in this data, two values or two levels, one is 12 meters and another one is 12.75 meters are given. So the general ground level, that is existing ground level at the proposed site of work, is about plus 11 meters, and the ground level below the proposed surplus slopes off till it reaches plus 10 meters in the about 6 meters distance. That means it shows the ground is sloping surface from plus 11 meters to plus 10 meters. So over a distance of 6 meters. Over a distance of 6 meters, the ground has a slope of 1 meter. Elevation difference is 1 meter, 11 to 10 meters. The tank bund has a top width of 2 meters at the level of plus 14.5 meters. So these are all, if you observe the relative levels, we can see here. Plus 14.5 meters is the level of the top of the tank bund with 2:1 side slopes on either side. The tank bunds are designed for a saturation gradient of 4:1 with 1 meter clear cover. That is the freeboard or clear cover is given as 1 meter. And also provision may be made to make the kacha regulating arrangements to store water up to maximum water level at the times of necessity. Generally for any tank, FTL means full tank level. So that is the normal water surface level in the tank in under ordinary conditions. Under extraordinary conditions, that means during the floods, etc., we can also store water some more height further beyond the full tank level. That is called maximum water level. So suppose if you want to store that additional water as additional storage in the tank, certain arrangements are required. So therefore in this present case also, provision may be made to make kacha regulating arrangements, that is temporary regulating arrangement, to store water up to MWL at the times of necessity. And also lastly, the foundations are of hard gravel at a level of 9.5 meters near the site of work. That means the foundation level or hard soil available at plus 9.5 meters. So this is the complete statement of the problem statement. So let me explain or repeat once again regarding this problem statement, from which we can extract the maximum information data for the design of the surplus weir. So here if you observe, the catchment area has given and also various levels, relative levels related to the structure are given. So if you see all these numericals regarding the RLs or reduced levels, so the lowest level is plus 9.5 meter, whereas the highest level is plus 14.5 meters. So that means the entire structure of this particular surplus weir under consideration is over a height of nearly 5 meters, 9.5 to 14.5 meters. So that means foundation bottom to top of the structure. So I hope it is the problem statement, it is clear. So anyhow, the entire information or entire data given in this problem statement has to be used for our design. Now coming to the design, let me explain the various steps or procedure of design of surplus weir that may be divided into various parts. So in this present video, I will try to cover 2 or 3 design components only. So the first one is the estimation of flood discharge. From the given data, we need to estimate the flood discharge, for which only we can design the surplus weir. So in general, for the estimation of flood discharge, most common formula is Ravi's formula. Ravi's formula is the most common formula to be used for the estimation of flood discharge. It's a very simple empirical formula which is given by Q is equal to Cm to the power of 2 by 3. Simple formula. You can see the flood discharge Q is equal to capital C and capital M to the power of 2 by 3, in which where C is the Ravi's coefficient, generally to be adopted depends upon the various factors like topography and nature of the area, etc. It may be in the range of 6.8 to 15. We can adopt appropriate or suitable value of Ravi's coefficient for applying this formula. So you should remember the range for this C value. It has to be assumed between 7 to 15 or 6.8 to 15. And the next important parameter is capital M. Capital M is the catchment area in square kilometers. Units are very important. So simply if you substitute the value of M in square kilometers, we will get the discharge in meter cube per second, that is SI unit directly. So you have to remember the units. While substituting the M value in this equation, the M should be in square kilometers only. So here 2 cases we have. So the tank for which the surplus weir has to be designed maybe comes under any one of these 2 cases. First case is if the tank is an independent one. So the independent means it has its own catchment area. That particular tank is called independent tank. And the other case is if the tank is a part of chain of tanks. Part of chain of tanks means so the entire area, catchment area is common or combined catchment area. Within that area, suppose if a number of tanks are there, that is comes under this case. So that is if the tank is a part of chain of tanks, number of tanks, one of the tanks we are considering. So if it is the case, the equation is slightly modified as Q is equal to similar formula. Cm to the power of 2 by 3 minus small c small m to the power of 2 by 3. If you observe carefully, both are same, C and M. Here also C and M. Capital C and small c, capital M and small m. Same. C is where M is the combined catchment area. You observe the difference. In the previous case, it is only independent catchment area in square kilometers. Whereas in the second case, since it is the part of chain of tanks, combined catchment area is to be taken as capital M. The small m is nothing but intercepted catchment area. So intercepted catchment area means the catchment area pertaining to tanks above the tank under consideration. So that has to be subtracted. So that's why carefully observe combined catchment area and intercepted catchment area. And small c is the Ravi's coefficient. It is a modified coefficient. It may be 20 to 33%. That means 1/5 to 1/3 of capital C. Like that we have to assume. Once if you assume the capital C value in the range of 7 to 15, from which we can easily determine the small c value also. Now coming to the given problem, earlier we observed the data of the problem. Accordingly, we have to calculate. So you see here one important point is this design of surplus weir, the complete design of various component parts etc. are to be discussed by taking a numerical example. Without numericals, there is no result. So therefore, simultaneously, by considering this present problem with numericals, we have to discuss the design of the surplus weir. Accordingly, for the given problem, capital M, that is combined catchment area, is given as 25.89 square kilometers, and intercepted catchment area is given as 20.71 square kilometers. So, and also assume the Ravi's coefficient C as 9. We can assume any value. Let us assume capital C as 9. Accordingly, small c is equal to 1.5. So by substituting all these values, we will get the value of discharge, that is flood discharge, as 67.45 cumex, 67.45 meter cube per second. Okay, it is the flood discharge, estimated flood discharge for the design of surplus weir. This is the first step for the design of the surplus weir. I hope it is clear. Next, coming to the major part of the structure, the major component part of the structure is design of weir wall. As our title is surplus weir, the weir is the major component. So therefore, weir in the sense weir wall. The complete design of the weir wall now we are going to discuss. So generally, any hydraulic structure, these walls as retaining walls are trapezoidal in shape. Stability point of view and safety point of view, the ideal section is trapezoidal section. Since it is having more stability, so therefore always we should recommend the wall or a structure in the form of a trapezoidal cross section. So here also the weir wall has to be assumed as trapezoidal shape. So therefore, in the design of the weir wall, we need to calculate or determine the total length of the weir wall, and then top width, bottom width, and also height. Since it is the trapezoidal in shape, we can assume like this trapezoidal shape. So which requires the dimensions like length, height, top width, and bottom width. Of course, side slopes are similar. So standard side slopes we can assume. Accordingly, we can design the wall. So coming to this procedure, how to determine the length of the surplus weir. So after calculating the flood discharge Q, and also by knowing the values of FTL and MWL, in the present case it has given already. Any numerical problem, they may provide the data like this. What is the full tank level, what is the maximum water level, like that. So from that given data, after calculating the flood discharge using the Ravi's formula, we can determine the total length of the weir wall using this formula. See here, one simple formula, you are all aware about this formula. This is the formula of a rectangular notch. Notches and weirs you might have studied earlier. Therefore, the same equation, whatever the equation for discharge through rectangular notch, same can be used for weir also. So therefore, the Q is equal to, see this equation, Q is equal to 2/3 CD L H root 2G H, in which CD is coefficient of discharge. You are all aware about that term, CD, coefficient of discharge. As the present case, the weir is a broad, let us assume it is as a broad crested weir. So this is another nomenclature or the type of the weir, depends upon the crest width. If it is more than 1 meter, generally we can treat it as the broad crested width. For the case of broad crested weir or notch, so we need to assume the CD value like this, 0.562. And the most important hydraulic parameter is H, where H is the head over the weir. Head over the notch or head over the weir, like that we are considering. So as Q is directly proportional to H. So in this case also, our H and Q relation we can see in this equation. So that's why H is the most important parameter. That can be obtained simply from the difference of maximum water level and full tank level. As it is the surplus weir, so unless otherwise specified, the water can be stored up to full tank level. That means up to the crest level of the surplus weir. If any excess water enter into the tank, that has to be discharged safely to the downstream side by means of this weir. That's why it is called surplus weir. So the head over the crest of the weir is capital H. So that is simply the difference of maximum water level and full tank level. Therefore, for the present problem, as Q is calculated at 67.45 cumex and MWL and FTL are given as 12.75 and 12 respectively. Therefore, the head over the crest is given by 0.75 meters. 12.75 minus 12 is equal to 0.75 meter. You remember one important point here. So in the most of the cases, in general, the head over the crest of the weir is not in the range of 0.75 to 1.5 meter only, not more than that. So therefore, in the present case also, it is around 0.75 meters only. So therefore, by using this equation and given data and certain suitable assumptions, we can obtain the value of length, the length of the, that is clear length of the weir wall as 62.45 meters. So this is the simple procedure to determine the length of the weir wall. However, in the present case, it has given the temporary regulation arrangements also required. So for which certain special arrangements are to be made, and also accordingly the length of the weir wall has to be increased. So therefore, how to determine the overall length of the weir wall for the present case? So here you see, since the Kacha regulating arrangements, that is temporary regulating arrangements, are to be made on the top of the weir to store water up to maximum water level at the times of necessary. So this is the necessary condition or requirement. So therefore, for which what are the arrangements required means, so we need to provide the shutters above the crest of the weir wall up to maximum water level. Accordingly, we will get the height of the shutter. So whatever the head over the crest of the weir, the same will be the height of the shutter. That is, in the present case, it is 0.75 meter height of the shutter is to be provided. Suppose if you want to provide such type of shutters, so number of shutters, we need to calculate how many number of shutters are to be provided. That again depends upon the size of the shutters. For convenience or easy to operate, even for manual operation also, the shutters are of a small size. Let us consider 1 meter width by 0.75 meter height, such that we can easily operate the shutters for lifting and lowering. In the present case also, so the shutters of size 1 meter by 0.75 meter are to be provided. If you decided to provide such type of shutters, so how many number of shutters are required and where these shutters are to be provided. So in general, for providing any shutter, certain supports are required. Those supports are in the form of dam stones. So here the grooved dam stones of size 15 centimeter by 15 centimeters will be fixed in the center of the crest at 1 meter interval with their tops at maximum water level. That means, so the size of each shutter is 1 meter only, clear size is 1 meter only. These shutters are to be provided successive dam stones. Those dam stones are having the grooves, so therefore we can conveniently operate the shutters manually, even manual also. So therefore, the clear length of the weir is already calculated as 62.45. Accordingly, the number of openings with 1 meter interval between the successive dam stones are 63, obviously. So for the factor of safety, let us consider 63 meter clear span is required to discharge the surplus water as per our requirement. So therefore, with this provision of shutter arrangement, the overall length of the surplus weir between the abutments is given by that 63 meter clear span plus the 62 number of dam stones. 62 means n minus 1. N number of openings are there, the intermediate supports are n minus 1. So therefore 63 minus 1, that means 62 number of dam stones are to be provided along the entire length of the surplus weir. Therefore each dam stone width is 0.15 meter, that is 15 centimeters. Accordingly, you will get the total length or overall length of the weir between the abutments as 72.3 meters. So therefore we have to provide an overall length of the surplus weir as 75 meters. So obviously always we have to consider some factor of safety. Accordingly, even though the actual length required is 72.3 meters, we are adopting 75 meters as the overall length. So like that, for any problem, for any numericals, the procedure will be the same. Accordingly, we have to determine, or we have to fix the total length of the weir wall. So one major dimension, that is the length, is over. Like that we can calculate. Now coming to the other dimension, that is height. How to determine the height of the weir wall? This is another next important dimension, obviously. So this height is height of the wall means right from the bottom to top, that is above foundation to top, that is crest level. Very simple. It is given in the present problem as a crest level as a plus 12 meters. It is given, which is incidentally full tank level. Crest level of the weir wall is nothing but full tank level of the tank. So in the present case it is 12 meters, and top of the dam stones or top of the shutters or maximum water level all are same, which is plus 12.75 meters. So therefore we are going to store an additional height of 0.75 meter only. And also the existing ground level for the present problem has given as 11 meters. You see all the values, numerical values, are reduced levels. Relative levels are given like that. And next thing is level at hard soil is available, that is below the ground level. Hard soil for foundation concrete, we need to excavate up to the hard soil. So therefore taking the foundations about 0.5 meter deeper into the hard soil, this is the general rule. So for a further factor of safety, we need to go for 0.5 meter deeper into the hard soil. That means even though the hard soil is available at plus 9.5 meters, further 0.5 meter we are going to down. So that means 9.5 minus 0.5, 9 meter is the bottom of the foundation concrete. Or in other words, we need to excavate for the construction of the weir wall up to a level of plus 9 meters. As the existing ground level is 11 meters, but the bottom of the foundation is 9 meters. That means we need to excavate 2 meter depth. Depth of excavation is 2 meters. Of course, the thickness of the foundation concrete, this is also as a standard as per specifications. Unless otherwise specified, the thickness of the foundation concrete should be 0.6 meter, that is 2 feet. So therefore, the level of top of foundation concrete is plus 9.6. We will arrive this value. So 9 meter is the bottommost level. So above which if you pour 0.6 meter foundation concrete, the top of the foundation concrete would be plus 9.6 meters. Now, simply we can calculate the height of the weir wall. So height may be given by the difference of top and bottom. So as the height of the weir wall, the top level of the weir wall, full tank level, etc. are 12 meters only, whereas the top of the foundation concrete is 9.6. Therefore 12 minus 9.6, which is equal to 2.4 meters. So therefore the total height of the weir wall, the total height of the weir wall from the top of the foundation to crest level is 2.4 meters. Like that we can calculate the, or we can fix the height of the weir wall. Similarly, after calculating the length and height, as it is the trapezoidal in shape, initially we assumed the cross section of the weir wall is trapezoidal shape. So after calculating the total length and height of the wall, and then top width and bottom width are to be calculated. So let us consider this crest width. Let crest width be small a, represented by small a. Generally the crest width is given by a formula. There is a empirical formula, one of the commonly adopted formula, that is A is equal to, that is crest width is equal to 0.55 root h plus root h, root capital H minus root small h. Again, what is capital H and what is small h? It is very clear that capital H is the height of the weir wall in meters, whereas small h is the head over the crest of the water, crest of the weir in meters. Both should be in meters only. So simply by substituting these two values, we will get the total crest width of the weir wall. In the present case, capital H, that is the height, just now we calculated as 2.4 meters, and small h is the head over the crest, that is maximum water level minus FTL, and that is 0.75 meters only. So therefore, by substituting these values, you will get the crest width, that is top width of the weir wall as 1.3 meters. Okay. Now coming to the base width. This is the another important dimension. Length, height, and then top width already calculated. Now how to determine the bottom width? This is somewhat complicated, or it requires some more lengthy calculations in the sense. So how to determine this base width? You see, this is the procedure to determine the base width. First thing is, the slopes of the weir wall on either sides being the same, in general, the base width B has to be determined from the stability analysis. Stability point of view, so or with respect to stability analysis, we need to determine the base width. So you are all aware, as per the stability requirements, so M suffix R, that is resisting moment, should be greater than or equal to overturning moment. For any case, for any structure, in general, stability analysis, you are all aware. So this is one of the requirements. Resisting moment should be greater than or equal to overturning moment. So in the present case also, if we consider M suffix O is the maximum overturning moment due to water thrust. So you see, in this surplus weir, so one side of the weir, the water will be stored. Therefore, the overturning moment is due to the water present, hydrostatic pressure on the upstream side of the weir wall. So therefore, this is another simple formula to be used for calculating the overturning moment is capital H plus S whole cube divided by 6, in which H is the, again same height of the weir wall, which is 2.4 meters in the present case, and capital S is the height of the shutter, that is again 0.75 meters. So by knowing these two values, we can easily calculate the overturning moment. This is simply we can follow this formula to obtain the overturning moment. Whereas the resisting moment is to be calculated based on the assumed section. This is somewhat complicated. So we need to use this lengthy expression or formula for obtaining the resisting moment. Of course, it is not required to determine the resisting moment, just to by applying this condition as a stability requirement, we can determine the base width. Our ultimate aim is to determine the base width of the weir wall. So you see, this resisting moment, expression for resisting moment consists of this base width, so which is a function of the dimensions of the weir wall. So therefore, if we observe this formula or equation, resisting moment is given by 1 by 12 into G plus 1.5 to the multiply with H plus 2.5 into S whole multiply with B square. Similarly, plus A into GH minus H into S into B minus half into A square into H plus 3S. So, though it is the lengthy formula or lengthy equation in which all the terms we know except this B only. So, you see, so where H is the total height of the weir wall, that is 2.4 meter. So, capital S is the height of the shutter, which is also known to us, that is 0.75 meter. And A is the crest width, already calculated it as 1.3 meter. And only unknowns are this capital G and B in this equation. We can calculate overturning moment using this formula, that is one value we will get. So that value has to be equated to this formula for stability requirement, as MR is greater than or equal to MO. So that's why just by equating these two values, we will get the value of base width B. The only thing is, we have to assume the specific gravity, value of specific gravity of the material. So generally these weir walls are constructed with masonry or concrete only. These are the two standard materials to be used for the construction of weir wall. So let us assume it is the masonry weir wall for which the specific gravity is given by 2.25. So these values are to be remembered. So you know that. So by the assumption that if you know the specific gravity value of concrete or masonry etc., then only we can apply this formula. So anyhow, take G value as 2.25 meter and crest width small a as 1.3 meter. Capital H is the height of the weir wall as 2.4 meter and capital S is the height of the shutter as 0.75 meter. With all these values, available values or data, we can determine the bottom width of the weir wall, that is small b, which is given by 2.4 meter. If you substitute and calculate, you will get this value of base width. In the present case, it is 2.4 meters. So therefore, I hope it is clear. Till now, we fixed the dimensions of the weir wall: length, height, top width and bottom width. See here. So finally, we have to represent the profile of the weir wall is like this. So as I discussed till now, we can see through this figure all the dimensions here clearly mentioned. The foundation concrete may be usually 0.6 meter thick. It is given here. After calculating the height, that is 2.4 meter, crest width A as 1.3 meter and bottom width B also equal to 2.4 meter, the profile of the weir wall is shown like this. You see, this is the height 2.4 meter, this is top width 1.3 meter, this is the bottom width 2.4 meter. Foundation concrete thickness is 60 centimeters or 0.6 meters. Accordingly, we have to represent the profile. You should remember, for every design component, we need to represent the diagram or figure like this cross-sectional view or profile. This is called profile of the weir wall. However, the overall length of the weir wall is 75 meters. Let us imagine perpendicular to this plane, perpendicular to this cross section, the 75 meter length of the wall is like this only. So, the next component is design of abutments, wing walls and returns. As part of the design of surplus weir, these comes under the protective works. A typical layout plan of abutments, wing walls and return walls is shown in this figure. You can observe carefully with this diagram or figure in which all the major components are mentioned. This is the body wall or weir wall. This is the tank bund. So just a line diagram only. So you see A, B, C, D, D, E and also A, F, F, G. So the from E to G or G to E, if you observe, this entire is a wall, like a retaining wall. So, but some terminology, abutments, wing walls and return walls can see here in this figure only. So, let us observe these component parts. So, with respect to this diagram, in which AB is the abutment. Where is AB? This is AB. Perpendicular to weir wall or body wall. Simultaneously, we have to observe the relative position, that is most important. So, where the abutments are to be provided, where the wing walls are there or where the returns, etc. So, this simple figure, the entire components will be observed. Okay, AB is the abutment and B to D is the upstream. This is upstream side, this is downstream side. Let us consider the water is stored in the tank here. So this is the direction of flow in this direction. So therefore accordingly this is the upstream side, this is the downstream side. Okay. So therefore this upstream wing wall is BD. BD is the upstream wing wall. Further it is divided into two parts, B to C and C to D. BC is the sloping wing wall, whereas CD is the leveled wing wall. So this BD upstream wing wall is divided into two parts or two categories, sloping and leveled. And also D to E is represent the upstream return wall. This is called return wall. Similarly, on the other side, that is downstream side, A to F is the downstream wing wall, which may be sloping one only, completely sloping wing wall, and F to G is the downstream return wall. So like that, this figure shows all the wing walls, returns and abutment on one side, one end of the weir wall. Similarly, in another end also, same set of components will be present. So, let us discuss the design of these components, abutments, wing walls and returns. In the present case, we will discuss these three components only. A typical abutment like AB. A typical wing wall, B to D upstream wing wall. Similarly, other side, other end also we have one more wing wall on upstream side. Similarly, on downstream side also, this is the wing wall on one end, and similar other end also we have another wing wall. This is called AF, is called downstream wing wall. Accordingly, DE is the upstream return wall, FG is the downstream return wall. I think it is clear, all these component parts. There are certain standard guidelines or specifications are there. Always we have to follow these standard guidelines. That is regarding these retaining walls. So abutment, as already mentioned, abutment, wing wall and return walls all are comes under, or we can treat it, they are retaining walls. So for which the top width of the abutments, wing walls and returns will all be uniformly 0.5 meter thick. The thickness, top width or top thickness of this entire wall is of 0.5 meter only, with a front batter of 1:8. So you remember this statement is a very, very important statement. Why? Because it is common for all the components. And that means the top width is uniform throughout as 0.5 meter only, half meter only, with the front batter of 1:8. Batter, that also already I mentioned. Batter means the vertical slope. So in the cross section you can observe the front side of that wall having the batter of slope of 1:8. That is the batter. And the length of wing walls must be enough to completely enclose the tank. But these wing walls, so how to extend? So how extend? We have to provide this wing wall on both sides, upstream side and downstream side. Means by satisfying this condition, we need to provide the lengths of the wing walls. So we have to consider the appropriate splays, and also this condition must be enough to completely encase the tank bund. So the length of the wing walls are in such a way that, so this end of the wing wall, both ends of the wing wall should be comfortably encased into the tank bund. So by keeping in mind these two standard specifications, we can easily design these three components. Just quickly I will go through this procedure. The abutment, how to determine, how to design the abutment means, so as shown in the previous figure, AB, that portion AB is called abutment. It has the top level same as that of the tank bund. Tank bund top level is plus 14.5. So these are all explained with respect to the numerical problem only, as I said earlier. So accordingly the numericals are like this. The top level of the abutment is same as that of the tank bund, which is equal to plus 14.5 meter. Its length at the top is same as that of the top width of the bund. So generally most of the cases tank bund top width may be a minimum of 2 meters. So therefore the length of the abutment at the top is equal to same as that of the tank bund top width, which is 2 meters in the present case. So therefore similar to the previous case like Wier wall, here also we need to design the abutment. Means we have to fix the dimensions of the abutment as a length, height, top width and bottom width. These 4 dimensions we have to fix. So length is same as that of the width of the tank bund. Is it clear? Therefore next dimension is height. How to determine the height? Simply the level difference between the top and bottom. So as per the existing conditions, the height of the abutment above the foundation concrete is given as top level is plus 14.5. It is clear. So that is tank bund top level. Yeah, according to the available foundation, the top of the foundation concrete is calculated earlier as 9.6 meters. So therefore this 14.5 minus 9.6, the 4.9 meter is the height of the abutment. Simply we can obtain the height. So simple elevation difference, level difference only. So and then after calculating the height of this is the procedure only. The only procedure to follow is like this only. First we have to fix the length. After length, height. Height is simply the difference of elevations. After obtaining the length, the bottom width required for stability point of view, it is another specification or another guideline as 40% of the height has to be provided as bottom width. For any retaining wall which is in general trapezoidal shape, after calculating the height with a certain fixed value of top width, the bottom width has to be provided as 40% of total height, whatever the height may be. So in the present case, the height is 4.9 meters. 40% of 4.9 means 1.96 meters. So let us provide 2 meters as the bottom width. Just to make it as round out 1.96 maybe 2 meters. Accordingly, we can fix the dimension. I think it is clear. Length is 2 meters, top width is 0.5, that is standard, and only height to be calculated as 4.9. After calculating height, we will get the bottom width. So then for this case also, we have to give or represent a small diagram like profile, which show in which all the dimensions and also relative levels are to be shown. So this is the case of abutment. Remaining all almost similar in nature, wing walls and also returns. You remember all these are like retaining walls only. So whatever the procedure to be adopted for the retaining wall, same can be adopted for this also. So anyhow, the wing wall, upstream wing wall, the portion BD is called upstream wing wall, and BC in which B to D, in between one more salient point, C is there. So BC is the sloping wing wall and CD is the leveled wing wall as shown in the previous figure. The section of the wing wall at B is same as that of the abutment. There is no doubt. So you suppose the section of the wing wall, see here, the section of the wing wall at B is same as that of the abutment. Already we designed this abutment AB. Whatever the section adopted for this AB, the same can be adopted for this wing wall also. That means at the starting point of the wing wall, that is at B, the cross section of this wing wall is same as that of the abutment. That is the statement given. How to go next. All right. So the section of the wing wall at B is same as that of the section at abutment. That is the meaning. Accordingly, the sloping wing wall BC starts sloping down from B till it reaches 30 centimeters above the maximum water. This is the another condition. This is point you should remember. Why it is sloping? Up to which extent we have to provide the sloping wing wall. Though the BD is the wing wall, in which BC is the sloping wing wall and CD is the leveled wing wall. So therefore, we have to fix that point C. So in such a way that, so maximum water level plus 30 centimeters. Maximum water level plus 30 centimeters. Right. Maximum water level plus 30 centimeter is the top of the wing wall. So that from that, that is in the present case plus 12.75 plus 0.3, 13.05. This is the this is the level of wing wall at C. Top level of wing wall at C is 13 point. That has to be continued further. So the portion of sloping wing wall BC will have its slope, top sloping down from 14.5 to 13.05. At B it is 14.5. At C it is 13.05. So you can imagine the sloping, nearly a 1.5 meter slope will be there. So accordingly we have to provide the sloping wing wall. See here the wing wall at C 13.05. The top level, height of the wing wall same 13.05 minus 9. This 9.6 is remain the same since the entire structure is at a single location. The hot soil is available at 9.5 meter. Accordingly, we fixed the top of the foundation concrete as 9.6. So therefore, this 9.6 is remains same for all the cases. Where only thing is top levels will vary. In the present case, for this section at C, top level is 13.05. Whereas the top of the foundation concrete is 9.6, that is bottom of the wall. Top and bottom levels are like this. Accordingly, the height of the wall is 3.45. So therefore, this height of the wall is 3.45 meter. Similarly, the remaining steps are similar. Bottom width is 40% of the height, 0.4 into 3.45. It is around 1.39 something. So therefore, provide 1.4 meter as the bottom width. Okay, and the last one is the remaining leveled wing wall and return. So that also you can observe here. See, from C to D and D to E, let us imagine this top level is same. That's why it is called leveled wing wall. 13.05. Just now we calculated as 13.05. 13.05 has to be continued throughout from C to E. So therefore from C to E we have to continue same. Since the level wing and return, that is the portion CD and DE have to be throughout 30 cm above MWL, the same section of wall at C, that is 13.05 at the top, can be adapted for both leveled wing wall and return. Similarly, downstream wing walls and returns also. Same procedure is adopted for downstream side also. Only thing, the point to be observed is, as the water after passing over the weir, it goes down rapidly to normal maximum water level in the water course. The downstream wings and returns need not be so high as those on the upstream side. This point we have to observe. Once again I will repeat. So when compared to upstream side, downstream side, the wing walls are not necessary to have that much height. Simple logic. The water is flowing down over the crest of the weir wall. So on the downstream side, water will spread over. We are not supposed to store the water on the downstream side. So therefore, these retaining walls or protective works are not required that much height. So therefore, the downstream wing walls completely from A to F will slope down till the top reaches the ground level. So existing ground level, up to the existing ground level, we have to maintain the slope. However, at the starting point it is same like 14.50 abutment cross section only. So from there we need to provide, see here, A to F and F to G. So in the downstream side, A to F completely sloping wing wall. So cross section at A we know abutment already designed, that is at a plus 14.5 meter its top. So from A to F we have to provide sloping wing wall complete up to existing ground level. Existing ground level in the present case it has given as 11 meters. So therefore let us imagine 14.5 here, 11 meters here. Nearly 3.5 meters slope down we have to maintain. Okay. So like that we can provide the sloping wing wall on the downstream side and also return. The section of wing wall at A will be same as that of the abutment. The top of the wing wall at F may be fixed at 11 meter as the ground level. So the height of here also one cross section we have to present. So height obviously 11 minus 9.6, that is 1.4 meter only. A typical cross section of the downstream wing wall is like this at F. So the base width is again 40% of the height, which may be 0.6 meter. So a small cross section we will get. The same section is continued for further FG also. So last one is the transitions. We have to provide the transition. So as already I mentioned the word splay. Splay is the angle of deviation. So see here the position of this wing walls on upstream side and downstream side with respect to the given splays. Upstream side the splay is 1 in. Upstream side the splay is given as 1 in 3, whereas the downstream side the splay is given as 1 in 5. So right 1 in 1 in 3 and 1 in 5. So that much deviation we have to provide. So that is called transition. So the reason is, in order to give an easy approach, the upstream side wing walls may be splayed at 1:3. Since you imagine the water will be stored in the tank, so therefore, so while approaching this weir wall, so smooth passage has to be provided. That's why the upstream splay is 1 in 3. That means 3 units in this direction, 1 unit deviated from this direction of flow. That is the meaning of splay. I already explained about the splay. Similarly, on the downstream side, not that much importance. We can provide the splay as 1 in 5. So 5 meters in this direction, 1 meter has to be deviated. That is called splay. 1 in 5 and 1 in 3. So these are called the transitions to be provided on the upstream and downstream side for a smooth approach. That's all. So thank you. With which we will stop here. The next part of this design will be continued in the part 2. Thank you.